Okay, students, the topic of synchronous machines continues, and the next example is related to a three phase 5 kVA, 208 volts, 4 poles, 60 hertz star connected. Uh, Again, it's a star connected machine, that means it is Y connected, which has a negligible stator winding resistance. So Ra is equals to 0. And the synchronous reactance X of S is equals to 8 ohms per phase at rated terminal voltage. At rated terminal voltage. And what is the terminal voltage? It's 208 volts for the terminal. The machine is first operated as a generator in parallel with a source. So first the machine is acting as a generator. Now what it wants is determine the excitation voltage. What is excitation voltage for a generator? It is the internally generated armature voltage EA. And the power angle, what is power angle? Power angle is the angle between the terminal voltage VT and the excitation voltage or the internal voltage EA. These are the two, this is the angle between these two voltages, and it determines the power flow in the machine. So we have to find out the internal generated voltage EA and also the angle between the voltage and EA when the machine is delivering rated kVA, that is the rated power of 5 kVA at this lagging power factor. So this means that the output current of the synchronous machine, that is the armature current, is actually having an lagging power factor, lagging angle. Draw the phasor diagram for this condition. So what is happening is that we have a machine, synchronous machine, and we also have this is the stator and this is the rotor, and it is acting, these are the three terminals A, B and C. This is actually this is a synchronous machine. So this is the stator, these are the windings A, B, C. This is the side view, and if you want to see the perspective isometric view, and this is the your excitation. So the voltage that will be induced in the winding inside the machine is EA, and the voltage that is at the terminal is V terminal. Now the students, it might be a point of confusion that sometimes the terminal voltage is equals to the internally induced voltage EA. That is only when it is an open circuit. When it is acting, when you have not connected anything with the terminals of the generator. But when there is a load connected, both these two voltages are not same. So the per phase equivalent circuit for our machine is actually, this is the per phase equivalent circuit of the machine. This is VT, this is RA, this is actually 0. So we consider it to be, this was very small, so we have assumed it to be 0. This is X of S, Gx of S, and this is actually equals to 8 ohms. And this is V terminal, and this is EA. Now what they have done is, so at this condition there is a load also connected with the machine. Now the load is connected, this is not open circuit characteristics, and with the load connected, he says that the machine is rated terminal voltage has negligible state and a synchronous 8 ohms per phase at rated terminal voltage. So the output of the machine has a rated terminal voltage that is equals to 208 volts. So the voltage that they have measured here is 208 volts. That is the rated condition is VT. But we realize the fact that this is a Y connected generator, so that rated terminal voltage is actually line to line voltage. It is between two lines. So we are making per phase equivalent circuit. We have to convert this 208 to terminal voltage per phase. So V terminal voltage will be then 208 volts divided by under root 3. So the value of this is 120 volts per phase. Okay, now the stator current, how to determine the stator current or the armature current for the machine. So this can be find out by the fact that the machine is delivering a rated kVA. So we know that our machine is delivering the rated output power, and the rated output power, the formula for a three-phase machine when is S rated equals to under root 3 V terminal, that is actually the line voltage in this case, not the, sorry, this can be V rated into IA, that's the output. So the armature current will be S equals to 5 kVA. Here we have this is 5000 VA. V rated is 208 volts, and this will be the current. So this will become 5000 divided by under root 3 into 208 volts, and this will become IA equals to 13.9 amperes. Now this 13.9 ampere is actually, there is the angle is the load angle is 0.8 lagging, which means that if we take cos inverse 0.8, so this will be actually 36.9 degrees. So if we look at these two values, then if this is V terminal equals to 120 volts at angle 0, then the armature current is IA equals to 13.9 amperes at angle 36.9 degrees, as it is a lagging condition. So this is how we have calculated this. If you are getting confused regarding this, this is the general formula. Now students, there might be a confusion that from where this equation comes. This is a three-phase power output of a generator, and you have known that this is either under root 3 V line into I line, or you have also read this formula as S equals to 3 V phase into I phase. So in Y connected generators, I line equals to I phase. There is the difference of these two voltages. Both of the formulas you can use to find out the IA armature current. So the armature current is actually, for the synchronous machine, it is coming out from the stator, and so this is this values of the current. Now what it is asking us now is that we have calculated these two values. So the per phase equivalent circuit, and if we look at the per phase equivalent circuit, the VT here, this is 120 volts at angle 0 degrees, and the current that is flowing through here is 13.9 with angle of minus 36.9. This current is flowing into the load. So applying simple KVL for the per phase equivalent circuit, we will have this equation EA equals to VT, that is at angle 0, plus IA J XS, and this is actually 120 0 plus what is IA, 13.9 angle minus 36.9 multiplied by JXS, that is 8, and because of J it is actually 90 degrees. And if we will solve this equation, then what we will get is EA, and in some books topologies it is also denoted as EF for the synchronous machine. It is so EA will become 206.9 angle 25.5 degrees. Okay, and so what will be the power angle? Power angle is actually the angle that is between the it is the angle between the voltage. Here we can see that its value is positive. It is the angle between EA and VT. Let's draw the phasor. It will make it more so for the VT, we had VT equals to 120 volts at angle 0 degrees, and the current was IA, that was equals to 13.9 with an angle of minus 36.9 degrees. So when we apply the KVL for the voltages, this is the VT here, and this part IA multiplied by JXS. So IA is like this, and the 90 degree phase shift, so here will be IAJXS. So the value of EA is actually here. This is EA, that is 206.9, 25.5, and here is the angle. Angle is positive, as you can see. The power angle is 25.5 degrees, that is delta, and this is actually 25.5 degrees. So this is the phasor representation of our circuit. Okay, so now the next part, we have concluded the part A. Now the next part is talking about if the field excitation current is now increased by 20%. This means that the current that is being supplied to our rotation part, that is IF, is increased by 20%. Now if it is increased by 20%, what will it increase? It will increase the flux inside the machine by 20%. And as the flux inside the machine is increased, then of course we know that the internally generated voltage, that is EA equals to K phi omega, if this is increased 20%, so this will also increase 20%. Internally generated voltage will increase 20%. So for this condition, that means that we have changed the field current for the generator, field excitation current. What is the stator current? What will be the current of the stator? That is the output current. What is now the power factor and reactive kVA supplied by the machine? To solve this problem, first of all, after our new condition, we can say that EA was, we calculated EA here. Now they have increased it to 20%, so it will also become 1.2 into 206.9, that is equals to, so EA dash will be, or EA prime will be 242.28 volts. This is after increasing the excitation current inside the machine. Now, despite increasing the excitation current, the load remains same. That the load is consuming the P. The P for the load will not be affected. Now the formula for synchronous machine, for example, this is our synchronous machine per phase equivalent. This is EA and this is VT, and here we have a load connected. Now what we have done is it is consuming P, a certain value of P at our rated terminal voltage. Now the excitation value is changed. So after changing the excitation value, the terminal voltage does not change. The P will also remain same. But what will change will be the value of EA. So this we have for our generator, the power transfer formula is for per phase equivalent circuit, it is V terminal into E armature over X of S into sine delta. So for both the cases, for the case as we know that P equals to P prime, so we can write this as Vt and EA over X of S equals to sine delta equals to V terminal. It will again remain same, but we have the internal generated voltage is changed, synchronous reactance is same, and also the power angle is changed. So if we compare these two values, we can see that this will become EA sine delta equals to EA prime sine delta prime. EA we have calculated in previously 206.9, and delta we know we have calculated previously, it was 25.5. EA prime we have calculated this, here it is 242. Now so we can calculate the new power angle that is between these the values will be 21 degrees. So this, why we have calculated this, you will understand this, that now the new power angle between these two value is 21 degrees. So the stator current can now be calculated by this formula. Similarly, as we have EA prime equals to V terminal plus IA J XS. So IA is equals to actually EA prime minus VT over Jx of X of S. EA prime is now the value is 242.8, angle is 21 degrees, and this is the angle that we have calculated from here, minus 120 volts, angle 0 degrees, divided by the X of S, that is 8 ohms, angle 90 degrees. So if we solve this, the value for IA can be calculated to be here is the space has ended. Let's see, IA equals to 17.86 with angle minus 51.5. This is the value of IA. And again we can see that the next part, it is saying that we should calculate the power factor. So the power factor will be, for the machine will become cos of the angle between the voltage and current, that is equals to 0.62, and as the sign of the current is negative, it is lagging power factor. Now to calculate the reactive power, the reactive power output from the machine, how much reactive power is being supplied by our generator, this can be calculated. If for the total reactive power, we can calculate this as Q equals to 3 for per phase equivalent circuits, Vt Ia sine sine theta. Theta is the angle between Vt and Ia, and so this will become 3 into 120 into 17.86 into sine 51.5 51.5 degrees, and this is actually equals to 5.03 kVAR. So this will be the value for the part B. Thank you. Okay, so the next part, what we have done up till now, we have calculated the excitation voltage for a certain load that was connected. Then we increased the excitation current for our rotor. And then in the third part, what it is doing is that the prime mover power is slowly increased. What is the steady state stability limit? What are the corresponding values? So for to understand this concept, it should be noted that for a generator, okay, this is our synchronous generator, and here is our prime mover that is actually giving us the mechanical power, and this mechanical power is connected to real power. And also there is another power, there is real power, and then there is reactive power generated by the our synchronous machine. Now in the second part, what they did was they increased the magnetic flux from the rotor. Okay, and what we saw was that for the per phase equivalent circuit of our machine, the real power remained same, but the reactive power changed for the machine, and due to the changing of the flux, and that's why the internally generated voltage was changed in the example B. Now in this scenario, what it is saying that prime mover is the power being delivered by the prime mover is being changed continuously. What is saying? Prime mover power is slowly increased. As this power is increased, so what are the stability limits? It means after what value the system will not remain stable. It is not possible that you can keep on increasing the mechanical power and the electrical output of it will also be linearly increasing. This is not possible. There will be a point after which the stability will change. So what is that actually? For that we know that there is a formula for the power transfer between the armature EA. We have seen this formula for a three-phase machine. This is EA into the terminal voltage VT divided by XS sine delta. And you would have also seen for sine delta. Now we know that the maximum power. Now what is this delta? This delta is actually angle between VT and EA. For maximum power to come out from this equation, when will we get P max? The P max value will be this 3EA VT over XS. This is only possible when delta equals to 90. So sine delta equals to 1, and we get this. This value means that the angle between the voltage, terminal voltage VT, and the internally generated voltage, that is delta, is now 90 degrees. When this is 90 degrees, we will be getting maximum power output. And what will be the maximum output power we can get from our machine? We have EA given. This is the EA that we calculated in part A, because it is saying that field current as in part A. So the value of this will become 3 into 206.9 and terminal voltage is 120 divided by 8, and this will actually equals to P max will be, our value 9.32 kilowatt. Okay, now this is 9.32 kilowatt, and once we have this value, we can calculate the value of IA. This is the maximum power, and for the IA we know that if we apply KVL here, let's calculate, we have to calculate IA, and the value of IA can be calculated as IA again is EA minus VT over JX of A, and in this scenario we know that it is 206.9, angle is plus 90 degrees. This is stability limits we are calculating. So, and this will be JX, not AXS, we can call it XS, and this will be 80-90 degrees. So IA value will become equals to 29.9 amperes. So what we were required were this maximum power transfer values. And now what about the power factor? Power factor, there I have missed something. Yes, 29.9 into 30.1. So this will be the value of current, and we can see that this is now the current angle is positive, and the per angle of the current is positive. So the power factor will be, power factor is cos theta, where theta is theta V minus theta I. V terminal theta V is VT angle is 0 and theta I is 30.1. So this with the angle would become 0.865 leading. This will be the power factor for the our system. And we can also solve this by drawing the phasors for our system. And once we have these values, similar way we can also calculate Q for the system. So this was a long question, but I hope it helps. Thank you. Assalamu alaikum.